Friends, welcome to lecture number 51 on surface drainage system design. So, in this lecture, we are going to see the a kind of design of surface drainage. For example, basically it has two components, one is hydrologic design and hydraulic design. So, in this lecture I will focus on hydrologic design. So, mostly finding out the the peak flow rate from a drainage area. Okay, so the basically these surface irrigation surface drainage, if you see, the surface drainage basically they removes excess water accumulated over the land surface in cropped area. Since we are interested in agricultural fields, so our focus is to remove excess water from the farmland. So, the surface what are the sources of this excess water? So, basically the rainfall, local runoff, okay. So, and then incoming water from adjoining higher area of seepage flow. Suppose this is kind of a base flow and excess irrigation water. So, when you apply a lot of irrigation water on top of the irrigated field, so definitely that is going to cause an excess water or generally the natural runoff, and then sometimes the the lateral seepage which is taking place from one field to another field. So, these they may cause the surface water ponding or water logging, or that requires surface drainage. So, the design of surface drainage consists of two stages. So, I said first one is hydrologic design and hydraulic design. So, hydrologic design basically involves the quantification of excess water to be drained and the rate at which it is to be drained. So, these two things we need to determine in case of hydrologic design, whereas in hydraulic design the design involves calculating the drainage channel geometry and the drainage network layout. So, once the channel geometry is estimated based on the peak flow rate, so then we are going to decide which layout basically we need to use. Okay. So, like parallel grid design or random designs, all these things we already discussed in the previous lectures. So, the next is hydrologic design. So, in this the estimation of surface runoff. So, the most famous methodology used to estimate the surface runoff is rational method. So, this is mostly common and empirical relationship. So, if you see, this is the relationship Q P, that is the peak runoff rate, which is equal to C I A by 360. So, this is the unit conversion in a way. So, where Q P meter cube per second, C dimensionless runoff coefficient, okay, and I is rainfall intensity for a given return period. So, generally we consider it as a time of concentration as a return period, and A is the area of catchment. So, that is hectares. So, I mean combining everything you get the amount of runoff taking place from the particular area, that is the peak runoff rate. So, that is the maximum or the peak and the maximum runoff rate you get from the area. So, basic assumptions in rational method are the uniform rainfall intensity for a duration at least equal to time of concentration. So, this is very important because this will lead to the time of concentration, definitely will lead to the peak runoff rate, and uniform. So, the rainfall should be uniform and also the intensity, though it should have uniform intensity throughout the area of watershed. So, the first thing is the uniform rainfall intensity of duration at least time of concentration. So, the second is the uniform rainfall intensity is throughout the watershed. Okay. So, these two basic assumptions we need to consider in case of rational method. So, next here a straight example giving the values and finding out the QP. So, let us see here the cultivated area. So, this is area is given, right, 40 hectares drained to a particular storm water inlet. The runoff coefficient for this drainage area has been estimated to be 0.4. So, this is C you got, and then based on specified design return period and the time of concentration of the drainage area, the design storm intensity has been determined to be, so 10 mm per hour. So, this is your I. So, what is the peak runoff rate from this area to be used to design the stormwater inlet? So, this is the equation QP is equal to CIA and QP 0.4, 10, 40 and 360. So, all values are given, they substitute it and you get finally QP is equal to 0.44 meter cube per second is the peak runoff rate we expect from the 40 hectare of land having a rainfall intensity of 10 mm per hour. So, then the next is, so what the procedure here, the rational method procedure. So, the first thing is the area of catchment. So, this is basically determined by surveying or from maps of aerial photographs. So, the area of watershed will be determined based on the maps or surveying or aerial maps or aerial photography. So, then the next parameter is the runoff coefficient, which is C. This is measure of rain which becomes runoff. So, this runoff coefficient will give the part of rainfall will become the runoff. So, in case of when C equal to 1, so that means the runoff is completely rainfall is completely turned into runoff, whereas if C equal to 0.1, so that means around 10% or you can say 9/10 of the rain may soak in, and so C equal to 0.1, right. So, C equal to 0.1 that means 10 percentage of the whole rainfall will become runoff. So, here there is a table you can use in order to find out the runoff coefficient C. So, the table has the topography on column number 1. So, this is a woodland, pasture, cultivated and urban area. So, there are different topography and vegetation on column number 1, and the soil texture on column 2, 3, 4. Okay. Column number 2 open sandy loam, column number 3 clay and silty loam, and column number 3 tight clay. So, based on these combinations like a particular topography and vegetation and the soil type, so you can decide the runoff coefficient. Okay. So, runoff coefficient if you see for tight clay, which results generally more runoff because less infiltration. So, the values are really increasing when you go from woodland to urban areas. Okay. So, similarly, in case of sandy, so the runoff the runoff coefficient is increasing, that means runoff is resulting higher in case of urban areas, right. And also the soils, if you see sand will have less runoff compared to silt and clay. Okay. So, that also you can clearly see here. So, and the next is rainfall intensity. So, the third parameter rainfall intensity. So, according to the desired return period for the design of the structure under the study. So, generally we are talking about the structures, we adopt the return period or the design procedure for designing a structure, soil conservation structure. So, similarly we use the rainfall intensity. So, the duration of the rainfall intensity is equal to the time of concentration of the runoff, or TC we call. So, here as I said in rational method. So, the basic assumption is the duration should be at least a time of concentration. So, here we in our design we are going to assume the duration is equal to time of concentration. So, generally for estimating time of concentration, so this Kirpich equation, so which is equal to TC is a function of the the drainage length and then slope. Okay. So, so this is the famous equation, you can remember it, or so the same equation, I mean you can translate into tabular form. So, here this is the maximum length of flow, that is the L, okay, this is L, and then time of concentration, this is the T c in minutes you get, and catchment slope S. So, knowing L and S, you get the what you call the time of concentration values. Okay. So, either you use equation or a table. So, both can work, and then so and then how to find out the rainfall intensities once you know the time of concentration, right, and how to find out the rainfall intensity. If you see the I mean the sorry, if you see the table here, I mean the picture here, right, the graph. So, duration in minutes, that is in T c, because our assumption is the duration is equal to time of concentration. Okay. So, then the rainfall intensity I in y axis, and if you see this plot, the curves, so those gives the return period. Okay. So, the return period, so knowing the return period and duration, that is the time of concentration, you can find out intensity. So, T c we estimated previously, I mean using previous equation or previous table. So, for 60, let us say for 60 minutes and then 20-year return period. So, you can expect a rainfall intensity is around 70, okay, around 70 mm per hour. All right. So, this way you can find out rainfall intensity. So, generally here we use the return periods for field structures 5 to 10 years we use, and gully control and small form dams 20 years and large form dams 50 years. So, based on these thumb rules we can select a particular return period, and for a particular time of concentration you can estimate the intensity in mm per hour. So, knowing area, intensity and runoff coefficient, you can find out the peak discharge from the particular area. So, here the example 2, so a catchment of 15 hectare is composed of 5 hectare of permanent pasture. The soil group of this pasture land is group B, and 10 hectare of row crop in poor condition. So, that is soil group C. Okay. So, what peak flow is to be expected from 1 in 5-year storm, right. The maximum flow length is 610 meter with a gradient of 2%. Okay. So, here the length is given, right, the maximum flow length L is given and S is given. Okay. Either you can use directly the formula, or from the table you can get. So, for example, here 610, so that may be here in between 500 and 1000, okay, and the corresponding slope is 2%. So, here you get around T c will be 12 minutes. So, based on the interpolation method. So, if you use interpolation method, you get around 12 minutes. Okay. So, that is time of concentration. So, one parameter is time of concentration estimated. So, using time of concentration and then the 5 years storm, that is a return period, and you can estimate the rainfall intensity. Okay. So, let us see how we estimate rainfall intensity here. So, this is the table, this is the return period, right, and then rainfall intensity, okay. And then so this will give, so rainfall intensity duration, so 10 minutes, 30 minutes, 60 minutes, 120 minutes. Okay. So, the maximum intensity you can get around 72 for 5-year return period. Okay. This is a 5-year return period, and then you get T c around 12, right, around 12 minutes. So, for 12 minute and 5 you get 72. So, or 72 or 73. So, this is also based on the interpolation. So, for this basically you need a 5-year return period and TC value. Using these two, you can find out the 73 mm per hour is the rainfall intensity. Okay. So, from this we estimated I, that is rainfall intensity. So, the next is the runoff coefficient. Okay. So, the runoff coefficient C for C. So, runoff coefficient C permanent pressure, there is another table, right, which is given by USDA, okay, or US SCS, US United States Soil Conservation Services. So, in this coefficient of C, for coefficient of C they gave two soil groups, group number B and group number C. So, here in this table, so the first column number 1 gives the cover and condition of the land, and then the soil group A, soil group B, soil group C and soil group D. So, A, B, C, D, so that is defined based on the infiltration capacity, right. And then if you see that, so group number B, so the C for permanent pasture. So, look for permanent pasture, this is here, okay, and the group B. So, this is a group B, right. And then here if you see the in the rainfall intensity rates, so that is around, I think what did we get? We get 70, we got 73, right. So, we got 73, so that might be somewhere here, and so that is corresponding value. Oh, okay. So, that is corresponding value for group B for 5 hectares. So, that will be 0.14 after interpolation. Here it is showing 0.17, but if you can interpolate that, you get 0.14. Similarly, runoff coefficient C for 4 let us say for 4 row crop. So, this is row crops 4 and soil group C, and here again 73 mm per hour, and you get around 0.71. Okay. So, then weighted C for all watershed is 0.52. So, that is 5 hectares into 0.14 plus 10 hectare into 0.71 divided by 5 hectare plus 10 hectare. So, if you can do this math, you get 0.52 is the weighted C. Substituting rational formula, so CIA. So, then QP is equal to, this is again unit conversion based on the units. So, the basically QP is equal to CIA. So, okay, so that is the, so based on the required units, that meter cube per second, and you need to multiply with the factor this. Okay. So, C 0.52, I 73, 15 is the total area, and QP is equal to 1.6 meter cube per second. Okay. And Cook's method. So, the Cook's method which is developed by US CES. So, this is United States Soil Conservation Service US SCS, and it provides a simpler. So, this is simpler than the rational method. So, or you can also Cook's method is a generalized rational method. So, the basically it requires the catchment size and the condition. So, these two, with these two things we will be able to find out the peak discharge. So, here the table, look at the table. So, take column number 1 is the conditions, that is the relief, soil infiltration, vegetation cover, surface storage. So, these 4 are the conditions, and the extreme peaks. So, the peaks are classified into 4 classes, right, extreme peaks, high peaks, normal peaks and low peaks. Okay. So, based on the peak type, so what the magnitude of peak, right. So, you have to, these are the weights basically 40, 20, 20, 20. So, if you can sum up all these 40%, 20%, sorry 40, 20, 20, 20 is that gives 100. Okay. So, similarly high peaks case, so hilly land slopes 10 to 30% you get 30, weightage, and slow to take water clays and low infiltration 15. So, like that you get 75, normal peaks 50 and low peaks 25. So, 25 is 10 plus 5 plus 5 plus 5. So, that will be 25. So, the maximum you get 25. Okay. So, this is called a catchment condition. Okay. So, catchment condition value. So, that is either 25, 50, 75, 100, or if anything is missing, so you can add accordingly. Okay. So, then the next step is, so once you know the catchment condition, so knowing the area, right, sorry. So, knowing the total value here, these are the total values, okay, and area. So, you can find out the peak flow rate in meter cube per second, right. So, this is the tabular method. So, when a total of catchment condition value is given and peak flow meter cube per second is estimated using this table. Okay. So, the next is SCS CN method. So, that is the soil conservation surveys curve number method. So, the method is based on the relationship between rainfall amount and direct runoff. So, basically the relationships are defined in series of curvilinear graphs, so which are called as curves. So, each curve represents the relationship between rainfall and runoff for set of hydrological conditions. So, hydrological conditions we have seen. So, there are 4 groups depend on the soil. So, soil group A, B, C, D. So, the soil group A is more porous and you get more infiltration compared to soil group D. So, the equation governing the relationship between rainfall and runoff is Q is equal to P minus 0.2 S square divided by P plus 0.85 into S, where Q is the direct surface runoff in depth units, that is mm, P is the storm rainfall in depth units, and S is the maximum potential difference between the rainfall and runoff in mm starting at the time of storm begins. So, when the storm begins, so the soil water reservoir, so soil reservoir, so which can accept the inflow, which can accept the infiltration, you can say, or losses or abstractions. Okay. So, that is S, right. So, here, so we have to find out S. So, S is a function of curve number now. If you see, so look at this. So, S, which is the parameter S is essentially composed of losses from runoff to interception or infiltration, etc. So, United States Soil Conservation Service calculated S by 25,400 divided by CN by 254. Okay. So, this is the finding out S value, where CN is the curve number. So, curve number generally varies from 0 to 100. So, if suppose curve number is 100, curve number is 100, right, S is equal to, if you substitute 100, so that will be so S will be 0. So, that means no storage. So, the mostly the rainfall is being converted into runoff. Okay. So, 100 assumes the total runoff rainfall, therefore, S equal to 0 and P is equal to Q. So, entire precipitation will be equal to your Q. So, the next is hydrologic design. So, curve numbers. So, here this table clearly gives the curve numbers for different soil groups. Look at this. So, column number 1, land use. So, land use, fallow row crops, small grain, okay. So, close seed legumes, pasture or range, permanent meadow, woods. So, all these things, and treatments are straight row crop or rows. I mean these fallow row crops, they are in rows or straight, or maybe so then contoured, terraced. Okay. So, all these treatments, and then condition is poor condition, good condition, poor, good, and based on the soil group. So, the curve number is been assigned. Okay. 77 is the curve number in case of soil group A. So, soil group A is more infiltration. Okay. So, if you see the curve number D, which has greater curve numbers, soil group D has greater curve number, that means more infiltration is less infiltration and more runoff is possible in case of soil group D. So, here the soil groups are defined. So, well drained sand or gravel, high infiltration rate, this soil group A. Soil group B, moderately well drained soil, moderate infiltration rate with fine moderately coarse texture, and group C, slow infiltration rate, moderate fine texture, and group D, very slow infiltration, mainly clay material, relatively impervious. So, that you get the curve numbers are close to 100. So, that the runoff, the rainfall mostly converts into runoff. Okay. And then let us see, and okay. So, there is also a table from where you can get the direct runoff. So, on x axis there is a rainfall, knowing the rainfall, and these lines are the curve numbers. Okay, so, curve number 100 and curve number 40, and y axis is the direct runoff. So, knowing the rainfall, for example, 8 is the rainfall, right, on let us say on 65 curve number, and then the corresponding runoff will be 4 inches here. Okay. Runoff will be 4 inches, and here this is 8 inches. So, out of 8 inches of rain, so 4 inch turns into direct runoff for a curve number of 65. So, here antecedent moisture content. So, AMC dry soil, AMC 2 average soil moisture, AMC 3 wet soil. So, this based on, so these curves will be adjusted based on the AMC values. So, generally for wet soil, because the soil condition, so the AMC is very important, antecedent moisture content. So, if suppose the soil is initially wet, so it results more runoff, right, compared to your AMC 2 and AMC 1. Okay. So, that is why here once we get the the direct runoff from the particular curve number. So, based on the AMC, it will be adjusted for particular AMC values. So, let us see an example here. So, this is an example. So, in a 300 hectare watershed, the curve number value was assessed as 70 for AMC 3. Okay, AMC 3 that is a wet soil, and estimate the value of direct runoff volume the following 4 days of rainfall. The AMC on July 1st was of category 3. Use standard SCS CN equations. So, the data given here is date and rainfall July 1, 2, 3, 4, and the corresponding rainfall in mm, and what would be the runoff volume if CN the category 3 value were 80. Okay. So, here CN 70, so what is the rainfall volume, and CN 80, what is the rainfall volume for the antecedent moisture content third. Okay. So, 3 category. So, here given the CN value is given 70. So, knowing the CN value, find out S using the 25,400 divided by 70 minus 254 will give 180.86 as S. Okay. So, the next is, once you knowing the S, you can find out Q value by using the formula Q is equal to P minus 0.2 S square by P plus 0.8 S. Okay. So, then find out here if you see. So, finally, you get equation like this, and on numerator P minus 21.78, right, which is square. So, here P should be at least 21.78, so that you get Q value, otherwise Q will be 0. So, that is why P should be 21.78, and if you can recall the precipitations July 1, 2, 3, 4. So, 50, 20, 30, 18 and So, the Q will be, so apply P here, right, only for 21 point, I mean P is greater than 21.7. So, not for this, right, not for this. So, and if you apply, if you substitute P value here, you get Q is equal to 5.81 and similarly 0.58, and the total will be 6.39 is the total runoff from that particular area, and corresponding to your curve number, okay, corresponding to the given curve number. And then the next, so there is the volume. So, the runoff volume of the catchment V r is equal to, so this is the area into the runoff depth. So, that will be giving the 223.65 meter cube. So, similarly for 80, right. So, given curve number, so find out S, so that is 63.5. Now, substitute this 63.5 in this equation. So, now, so this is the equation. So, now the Q value, I mean P value should be at least 12.7. So, now from the table, again we now bring the table and see and find out the so now all precipitation values are going to result runoff in this case. Okay. So, now you see 50 substitute P in that previous equation, you get 13.8 and 20, which is 12 more than 12 point, and 18 also more than 12 point. So, here the total runoff depth would be 18.66 and the total runoff over catchment V r is equal to 350 is the area cross area, and then so this is the depth and you get 65310 meter cube is the runoff volume. So, for increasing curve numbers, the runoff volume is increasing. Okay, look at this. So, this is all the lecture about hydrologic design of surface drainage system. In the next lecture, we are going to talk about the hydraulic design of surface drainage system. Okay, thank you.